In today's video, we are going to be talking about this very interesting topic, electrolysis. Now, before we talk about electrolysis, let's talk about some terminologies. What are electrolytes? And electrolytes or electrolytes are compounds which conduct electric current either in aqueous solution or in multi-state, while non-electrolytes are compounds that do not conduct electricity either in aqueous solution or in their molten state. Now let's talk about electrodes. Electrodes are rods, wires through which electric current enter into the solution, all right, or enter into the electrolyte. Electrodes are categorically divided into cathode and anode. Cathodes are negatively charged electrodes, and anodes are positively charged electrodes. Now, what is electrolysis? Electrolysis involves the decomposition of ionic compound, that is the electrolytes, into their ions by the passage of direct current through the solution or molten form of the compound, followed by the corresponding discharge of these ions at the electrodes. Now let's have this typical diagram of electrolysis. Now what happens here is that this is the electrolytes. This is the solution. And here is the direct current source. And this is the cathode, which is the what? The negatively charged electrode. And here is the anode, the positively charged electrode. And so once this direct current source is turned in, the current flows into the solution through these electrodes. And what happens is that this electrolyte will decompose to its ions, the constituent ions. And when they decompose to the constituent ions, these constituent ions, some are positively charged, and some are negatively charged. So the cations, which are the positive ions, will migrate to the cathode. Cations migrate to the cathode. And the anions, which are the negatively charged ions, they will migrate to the anode. Cations to cathode, anions to the anode. All right. So, and then the cathode or the anode will now want to discharge the ion that migrates to its side. All right. I believe you understood what happens in electrolysis now. Now, when these ions migrate to the respective electrode, there are some factors that will determine which ion is preferentially discharged. And the factors are: number one, the position of ions in the electrochemical series. And number two, the concentration of ions. And number three, the nature of the electrode. We are going to study this systematically, and in the course of this tutorial today, you are going to be learning a lot of things in each of these factors. So if you have not subscribed to this channel, I want you to hit the subscription button, turn on the notification button, and also give us a like in of this video and share the video with your friend. We have a lot of videos, interesting topic that we've explained well and good for you in this channel. Now, the factor number one, the position of ions in the electrochemical series. Now, you can see here is potassium, sodium, magnesium, aluminum. Of course, we can still have calcium before the magnesium, all right? Aluminum, zinc, iron, and so on and so forth. Here is at the series. Let's just have this. Now, increasing order of preferential discharge. That means this silver and gold here has the highest priority of being discharged, because so let's have a solution whereby the competing ions is copper 2 plus and H plus. Okay, so because copper is below hydrogen in the electrochemical series, so therefore you say that copper will be preferentially discharged. The energy required for you to discharge copper is less than the energy required to discharge hydrogen H plus, all right? So therefore, you say that copper 2 plus is preferentially discharged. Now, here are the anions. Now, the order is opposite, all right? So anions are the anode. If OH minus and Br minus are the competing ions at the anode, then the priority will be given to OH minus. All right. Okay. Now let's talk about the factor number 2, and that's the concentration of the ion. If all other conditions are equal, increasing the concentration of a given ion tends to promote its discharge. But this factor is effective if the competing ions are closely positioned in the electrochemical series. For instance, you're talking about the electrolyte, an instance whereby OH minus and Cl minus, for instance, are the competing ions in the solution. If the concentration of Cl minus is so high than that of the OH minus, then because they are closely positioned in the electrochemical series, that means when one or two ions separate them, then that of the concentration factor can overrule the position, the factor of position in the electrochemical series. So for instance, whereby we have Cl minus being far more concentrated than OH minus, the Cl minus should be preferentially discharged to OH minus. Now, but if you are having between OH minus and NO3 or any of these other ones, you see that they are far in the electrochemical series. They are farther from each other. They are not closely positioned in the electrochemical series. So the factor number 1 still takes the precedence. All right. Now, this factor is well understood when you compare the electrolysis of dilute sodium chloride solution and that of concentrated sodium chloride solution known as brine, and you are going to be getting this more. All right. Now let's talk about electrolysis of dilute sodium chloride solutions. The first thing, whenever you want to talk about the electrolysis of a particular solution, the first thing you're going to be talking about is what are the ions present in the solution? What are the ions present in the solution? Of course, you're talking about sodium chloride. You know that sodium ion will be present, chloride ion will be present. Then because water was used in the dissolution, then H plus and OH minus will be present. All right. Now, what are the ions that will migrate to the cathode? Of course, you can remember that cations will migrate to the cathode, and these are the cations. Then the anions will migrate to the anode. All right. So Cl minus and OH minus are the anions, and they will migrate to the anode. The cations are the what? Na plus and H plus. They will migrate to the cathode. Now, which one will be preferentially discharged? You go to the position of ion in the chemical series, you see that H plus is far below sodium ion. So therefore, you find out that H plus that is far below sodium ion will be preferentially discharged. So therefore, at the cathode, you said that the 2H plus, of course, this is the way you write the reaction. Okay, you say that H plus will be partially discharged and it's going to give you hydrogen gas, and you balance the equation. And so you say that is your equation, the cathodic reaction. Cathodic reaction is usually written for the ion that is preferentially discharged at the cathode, while anodic reaction is written for the ion that is preferentially discharged at the anode. All right. So at the anode, of course, we have these two, and you say that this one will give us oxygen. All right. So this, whenever OH minus is being discharged, is preferentially discharged, this is the equation that you're going to write. All right. So now you can tell us the respective nature of the resulting solution. Of course, you know that Na plus is left, and also Cl minus is left. So the resulting solution will be a more concentrated sodium chloride solution since Na plus and Cl minus are left. So to form concentrated sodium chloride solution. All right. Now let's talk about the electrolysis of brine. The electrolysis of brine. All right. So now in this place, we can use platinum electrodes. You cannot use graphite electrode or carbon electrode. Why is it that you can't use carbon electrode in the electrolysis of dilute sodium chloride? The reason is because oxygen is being given off at the anode. And so if you use carbon electrode, which is graphite electrode, as your anode, then the oxygen is going to be burning the carbon. And when carbon, which is graphite, reacts with oxygen, is going to give CO2. And the CO2 will dissolve in the solution to produce a resulting acidic solution. And so you have to constantly replace that of the anode. And so that's why graphite is not the best electrode to use for the electrolysis of dilute sodium chloride solution. We use platinum electrode. All right. Now let's talk about the electrolysis of concentrated sodium chloride solution. Here we can use carbon electrode. I'm going to tell you that later. Now, the ions present in the solution is still the same, but here the solution is concentrated, which means that the sodium plus and the Cl minus are more concentrated than the H plus and the OH minus. All right. Of course, at the anode, these cations will migrate to the cathode, and at the anode, we have the anions, which are what? Cl minus and OH minus. Now, of course, here, though sodium chloride, sodium ion is more concentrated than hydrogen ion, is not yet still preferentially discharged because the two of them are not are not closely positioned in the electrochemical series. So therefore, the H plus, which is still below sodium, the electrochemical series will be preferentially discharged. And so therefore, we still have this as the reaction that is happening at the cathode. Now at the anode, the Cl minus, as I explained earlier, is closely positioned with OH minus. And this time around is also more concentrated. Therefore, the Cl minus will be preferentially discharged. It is not the OH minus that will be preferentially discharged. So the Cl minus will be preferentially discharged and given out as chlorine gas. All right. So the resulting solution is what now? The resulting solution will be sodium hydroxide because OH minus is left here, and at the cathode, this is left behind. And so the two of them will form NOH solution. And so that is a basic solution. So the resulting solution will be basic. Now, so therefore, if you compare the electrolysis of concentrated sodium chloride and that of the dilute sodium chloride solution, you're going to see at the cathode, OH minus, hydrogen gas is given off just like also in the electrolysis of concentrated sodium chloride. But at the anode, here OH minus is preferentially discharged, but here chlorine is preferentially discharged due to the concentration effect. All right. And also the solid solution here is a concentrated sodium chloride, while here the solid solution is a base, is sodium hydroxide. And this is how electrolysis is used to prepare important chemicals. That's one of the applications of electrolysis. All right. Now let's talk about the nature of the electrode. Now, the nature of the electrode is very important in electrolysis. And that is because the nature of the electrode influences the reactions a lot. It affects the electrolytic reactions. Now, for instance, in the electrolysis of sodium chloride we talked about earlier, if you use mercury electrode, instead of hydrogen being preferentially discharged at the cathode in both cases, you'll find out that sodium will be preferentially discharged because mercury has such a high affinity for sodium, and therefore sodium will be preferentially discharged. You say, oh, my long time friend, oh, you are the one I'm going to preferentially discharge. Okay, that's very interesting. Yeah, it has an affinity for sodium. Now, here we're going to be talking about active electrode and inert electrode. An active electrode is an electrode that can participate in an electrochemical reactions or electrolytic reactions. I'm also going to explain active electrode as an electrode that has its ion present in the solution. Do you get what I mean by that? I mean that when the anode or the cathode is a metal in which the electrolyte is the solution of its salt. What I mean is, for instance, if you are doing the electrolysis of copper sulfate solution, this solution is copper sulfate. And you are using copper electrodes, that means as the anode, as the cathode, that then these electrodes will be active. They are going to be active because the metal or because the electrolyte is a salt solution of the what? Of the uh, metal of the electrode. Now you are doing the electrolysis of silver nitrate solution and you are using silver as the anode or the cathode. Therefore, the silver will be active. It's going to be an active electrode. All right. So now, but when you are doing the electrolysis of copper sulfate solution, and let's say this one is platinum, yeah, and this one is copper. So now this is copper sulfate solution. This copper will be active because its ion is present in the solution. Now, but here is copper sulfate solution, and you are using platinum. This platinum will be inert. It will be an inert electrode. This one will be an active electrode. Now, there's something that is very, very crazy about electrolysis. The moment when anode is active anode dissolves during electrolysis. So that's what you should put at your fingertips here. Once the anode is active, it's going to dissolve. And the versatility of this knowledge has been applied in electroplating, in purification of metal, which I'm still going to talk about, and many other applications of electrolysis because of the fact that once the anode is active, it will dissolve. It will dissolve. All right. Now, let's talk about a very popular example. That's when you're talking about the electrolysis of dilute copper sulfate solution using platinum electrode and when you're using copper electrodes. Now, let's talk about that. Now, the case whereby the anode and the cathode, that means the electrodes, both the cathode and the anode is platinum. And of course, in that case, you know that both the cathode and the anode are not active. They are inert electrode. So the ions that are present in the solution, copper itself, copper 2 ions, SO4 2 minus from the salt, then this one from water. Now at the cathode, we're going to be having the Cu2 plus and H plus. And of course, the copper is below hydrogen in the electrochemical series. And of course, the copper 2 plus will be preferentially discharged. At the anode, we have the OH minus and the SO42 minus. I'm sorry about that. Sorry, this is supposed to be SO42 minus. SO42 minus ions. And of course, OH minus is going to be preferentially discharged. And so we have this. And the nature of the solid solution, the solution is going to be, of course, when you see copper sulfate solution, a copper sulfate solution is actually a blue solution. The reason why it's blue is because of the presence of the copper 2 ions. The copper 2 ions is what is responsible for the blue coloration of copper 2 tetrasulfate 6. uh, copper 2 sulfate 6 solutions. All right. So you see why copper sulfate solution is blue is due to the presence of copper 2 ions. And now that at the cathode, the copper 2 ions is progressively discharged, what happens is that the solution turns from blue to fade blue and then will ultimately become clear. All right. And also the solid solution will be acidic. Why will it be acidic? Because here copper 2 has gone. Here at the cathode, copper 2 has gone. At the anode, OH has gone. What do you have left? This. You can see another solution, another important compound or chemical produced during electrolysis. SO4 2 minus will be left behind. And because H2SO4 is left behind an acidic solution, an acidic substance, therefore the resulting solution will be acidic. So you're doing the electrolysis of copper 2 sulfate, the solution is going to turn from blue to clear, and then it's going to become acidic. Now let's talk about the electrolysis of copper 2 sulfate using copper electrode. And this time around, we are using copper electrode, and it's going to be an active electrode because here you are doing the electrolysis of copper sulfate, the solution of the salt solution of copper, and you're also using copper electrode. So in that case, the electrode is going to be active because its ion is present in the solution. All right. So of course, you first ask the question, what are the ions present in this copper sulfate solution? You're going to be having copper 2 plus, SO4 2 minus, H plus, and OH minus. And cations will migrate to the cathode, and anions will migrate to the anode. So therefore, at the cathode, we have CO2 plus and H plus, and at the anode, we have OH minus and SO4 2 minus. Now let's talk about the cathodic reaction. Of course, we know that the copper being lower than H plus in the electrochemical series is going to be preferentially discharged. And so therefore, we have this equation as the cathodic reaction. Now, what about the anodic reaction? This time around, you could remember I told you earlier that when you are using an active electrode, once the anode is active, it's not going to discharge any of the ions that migrate to its side. Rather, it will dissolve. So therefore, the copper rod anode will dissolve. And when it dissolves, it joins the copper 2 plus ion present in the solution, and it will both migrate to the cathode for deposition. So therefore, what happens in the electrolysis of copper sulfate is that we have the dissolution of the anode. Unlike when we are using an inert electrode, we see that the normal reaction we occur. All right. So therefore, if we want to talk about the nature of the resulting solution, of course, we see that this will still be present in the solution. This one will be present in the solution, and this one will be present in the solution. The solution will be relatively acidic, but the blue color of the solution will remain unchanged because you're having some copper 2 plus leaving through the cathode, and you have another one coming from the dissolution of the anode. So therefore, the solution remains blue. Okay, so now we'll be going to all right, Faraday's laws of electrolysis. Let's talk about Faraday's first law of electrolysis. The first law of electrolysis by Faraday states that the mass of an element deposited during electrolysis is directly proportional to the quantity of electricity passed through the electrolytes. Or we can also say that the volume of gas that is liberated during electrolysis is directly proportional to the quantity of electricity passed through it. Now let's talk about the mass in terms of mass deposited of an element. Okay, now the law says that the mass of an element is directly proportional to the quantity of electricity passed through it. It then means that the mass equals to ZQ, where Z is known as electrochemical equivalence. And this electrochemical equivalence is known as the atomic mass of the element divided by the coefficient of the electron in the electrolytic reaction. All right, so let's make this one equation 1, and then this one equation 2. Then we can also recall that the quantity of electricity is actually equals to IT. All right, so if this is equation 3, so if you substitute equation 2 and 3 into equation 1, then we're going to have the mass of an element. So substitute 2 and 3 into 1. So what do we have? Then it means that M equals to over EF. All right, so this M is mass of element deposited during electrolysis. This capital letter M is known as the atomic mass of elements deposited during electrolysis, the atomic mass, which is usually a constant. All right, so I is current, T is time in seconds, and E is the charge on element, and also you can say is the coefficient of electron in an electrolytic reaction. And so F is Faraday's constant, which is 96,500 coulombs. All right, so that is the equation we're going to be using to solve problems on Faraday's law. Due to the volume of gas given off. So the volume of gas given off, we also follow the same formula. So, but this one will be volume at STP IT over EF. So see the same derivation. All right. So this volume at STP is usually 22, that's 22.4 dm cube. So he is the volume, the coefficient of electron in the balanced equation. All right. So this small letter V is the volume of gas given off or liberated. Let's go to the first example under Faraday's first law. The first example says that 2.3 milliamperes of electric current is passed through the solution of a dilute copper sulphate for 2 hours, 15 minutes, 10 seconds. Calculate the mass of the element deposited at the cathode and the volume of gas given off at the anode. All right, so what we have here is the mass of copper. Of course, we're talking about the electrolysis of copper sulfate. This time around, you're talking about volume of gas given off, then it means that platinum electrode is used. And so at the anode, at the cathode, we find out that it is copper that will be given off. So the copper ion in the solution will take 2 electrons to give us copper solid. So here is the electron. So therefore, write our formula M equals to MIT over EF. So this small letter M is the question. the atomic mass of copper is usually 63.5 or 64, and I is 2.3 milliamperes, so which is actually 2.3 times 10 raised to the power minus 3 amperes. And the time, which is 2 hours, 15 minutes, 10 seconds. So when you convert that to seconds, of course, that's going to give you 8110 seconds. And the E here so the E is actually 2. So that's the coefficient of the electron or the charge. So the coefficient of electron in the balance equation or in the electrolytic equation, that's going to be 4. All right. So, and F is the Faraday's constant, which is going to be that. So what do we have? We have that mass is going to be 63.5 times 2.3 times 10 raised to the power minus 3 amperes, then times time, which is 810 seconds. So divided by the E, so that means the coefficient of electron, which is 2 times 96,500. All right, so what do we have? If you press your calculator, so we're going to have 0.0064 gram of copper deposited at the anode. Sorry, 614. All right, so let's calculate the volume given off at STP. Now the volume at STP, I and T divided by EF. So, of course, the volume at STP is a constant, that's 22.4 dm cube. So, times I, we already know what I is, that's 2.3 times 10 raised to the power minus 3. And then the time is 8110. Then the E, all right, sorry for not writing the electrolytic reaction. That's the first thing you should always do. And of course, you know, the volume, the gas that will be given off in copper sulphate is going to be oxygen, because at the anode we will have OH minus, just as I explained earlier, and the SO42 minus. So this one will be preferentially discharged, and that's going to be 4OH minus, giving us 2H2O plus 1 mole of oxygen plus 4 moles of electron. So therefore, the key here is going to be the mole of electron, which is 4 times 96,500 coulombs. And that's going to be 1.1 dm cube. Question number 2. 1.2 gram of element X is deposited as cathode when 0.6 amperes of electric current is passed into the solution of the salt for 1.5 hours. What is the charge on element X, given that 1 Faraday is this and the atomic mass of the element is this? All right, of course, we say let N be equals to the charge of the element. So if we are writing the reaction for the electrolysis now, the cathodic reaction, I mean, so you're going to have Xn plus N of this to give us this. Of course, it will come out in form of solid. Okay. So now, of course, there is a mark for this. Now, we can remember our formula. M equals to the atomic mass multiplied by the current and time in seconds. all over. So this one is the moles of this electron here, and this one is the Faraday. All right. So M is 1.2 gram. So, and the capital letter M, you can remember that it is the atomic number of the element, so which is 65 gram per mole. So I is 0.6 amperes, and the time, which is the time T, is actually 1.5 hours. So which you are going to convert to seconds. So that's 1.5 to 60. Then as to minute, then from 60 minutes to seconds. So times 60. All right. Now, so the E now, so is the coefficient of the electrons, so which represent the charge. So whenever you are calculating the charge on the element, so you'll be looking for X. All right. So whenever you're calculating the charge, you'll be looking for E in this equation. So F is 96,500 coulombs. I believe that is very simple. So therefore, in calculating the charge, we make E the subject of the equation, so that E now is going to be MIT and over MF, so which is 65 times 0.6 times 1.5 times 60 times 60 divided by 1.2 times 96,500. So which is approximately 2. So the charge, before I continue to talk about Faraday's second law of electrolysis, I would like to share something very important with you, and that is from the book of Mark chapter 11 and verse 1 to 9. I didn't write all the verses here. I just want to bring out this verse as a lesson. But from verse 1, we saw Jesus Christ sent his disciples to go and bring him a cart, so that he could ride upon the cart to Jerusalem. Now, when his disciple got there, they brought the cart. And in verse 7, and they brought the cart to Jesus, and they cast their garment on him, and he sat upon him. And many spread their garments in the way, and others cut down branches of the trees and strewed them in the way. And they that went before and they that followed cried, saying, Hosanna, blessed is he that cometh in the name of the Lord. Now, what can you see here? What the Holy Spirit wants me to point your attention to here is, and many spread their coats in the way, and the court began to walk on the garments that the people laid on the way. Many people cut down branches so that the court does not walk on a dirty ground. Now, the story of the court changed immediately. People cast their garment in the way. People cast their garment on the court. They began, the court was decorated. The court became beautiful, and it was not walking on the mere ground. That's what happened. The court, these disciples were sent to bring the court, and the court came to Jesus. So also, Jesus has sent me to you today to go and call you, that he wants to make use of your life. Jesus has called me, has told me to go and tell you that he wants to make use of your life. He just wants you to surrender your life to him, just like the way this court surrendered. And this court was beautified. Jesus wants to beautify your life too. Will you heed to Jesus today? Will you give your life to Jesus? Will you come to Jesus so that he beautifies your life? Will you serve Jesus so that he can make you beautiful in life? So that as you are publicizing his glory, your life changes. I've seen many people, the day they gave their life to Jesus, their brain opened. They began to do what they couldn't do before. They began to understand difficult, complex subjects that were difficult for them. Jesus opened their brain and they began to serve Jesus, and today they are in great places. And ultimately, they will escape hellfire, because hellfire is the end of life without Jesus. If you don't have Jesus in your life, if you don't believe Jesus Christ as the Lord and Savior, if you don't accept Jesus as the Lord and Savior, and you don't pray day by day to be like Him, then you have signed for hellfire. I pray that you'll be wise today in Jesus' name. Jesus, thank for this person that has heard your word and he wants to give his life to you. He wants to serve you. I pray that you accept him and help him and let your name be glorified in his life and destiny. In Jesus' mighty name, I pray. Amen. I go to Faraday's second law of electrolysis. Let's go to Faraday's second law of electrolysis. What is Faraday's second law of electrolysis? It states that when the same quantity of electric current is passed through different electrolytic cells connected in series, the amount of element deposited in each cell is inversely proportional to the charge on the elements. So, of course, if we're going to be doing that, the law says that, as mathematically, the law says that it's inversely proportional to the charge. All right? So the charge on the element. And of course, earlier, we deduced that this charge is the same as the coefficient of the electron that is passed. All right, so let's use, so where C is charge, and we'll represent it denoted by E. All right, so which is the E. So therefore, we will find out that the amount in moles is going to be equals to K over E, and so therefore Ne is a constant. So where this constant is quantity of electricity measured in farad, the quantity of electricity measured in farad. Okay, so therefore, if N is a constant, then it means that N1, E1 is N2, E2. So where N is amount of elements in moles. And we can remember that mole is mass over molar mass. That's mass over the atomic mass. So this is small letter m, please. This is small letter m, and this is capital letter M. All right. So I'm trying to say that this mole, excuse me, sorry, this mole is mass over the atomic mass. So this is small letter m, this capital letter M. All right. So it's also equals to volume over volume at STP. Okay. So it means that the mass of element 1 divided by its atomic mass, then the charge on the element is equals to the mass So that is the second law of Faraday. Second law of Faraday makes it very easy for us to compare the different masses of elements produced in different cells, in different electrolytic cells. All right, when the same quantity of electricity is passed through both cells. Okay, so now let's have a question. Let's have an example. Example number one says that what mass of zinc will be deposited by the same quantity of electricity that deposited 5.28 grams of silver, or from AgNO3. All right, so solution. Now, what happens here is you are also compare, you also find the mass of zinc that is produced by the same quantity of electricity that produce silver. So it means you'll be using second law of Faraday to make life very easy. So we just compare that the mass, the first one is zinc, so the mole of zinc, the electron passed in zinc electrolytic cell is mole of silver. Then this one is silver. All right, so of course you write the equations, so you know that zinc, and it's going to be at zinc 2 plus 2 electrons is going to be produced zinc solid. And therefore the silver is silver plus an electron to give us silver. Okay, so you can see that here the most of this electron is 2. So the electron is 2, the charge is 2, so the electron is 2. Okay, so here 1 mole, so the charge is 1, so the electron pass is 1. All right, so therefore for this equation 1 can be written as, since this one is mole, so which is mass of zinc over the atomic mass of zinc multiplied by E of zinc equals to the mass of silver over the atomic mass of silver, the electron passed in silver electrolytic cell. So, of course, you find out that the mass of, so what is, that's the unknown. So mass of zinc is the unknown. The atomic mass of zinc is 65, and the electron passed is 2, So then the mass of silver, which is 5.28 all over 1 divided by 108, that's the atomic mass. Then the electron passed is 1, so because the charge is 1. All right, so therefore we make the mass of zinc the subject. So what do we have now? That's going to be 65 times 5.28 times 1 divided by 2 times 108. All right, so if you calculate everything, if you press it on your calculator, so we got to have that the mass of zinc that we produced is 1.59 gram. All right, I believe that's very simple. Now let's go to the last question. The question says that a quantity of electricity deposited 3.2 grams of aluminium. Calculate the volume of oxygen that will be produced by the same quantity of electricity. All right. So of course, we're going to be comparing the mole of aluminium, and the charge of aluminium equals to the mole of oxygen and the electron passed in oxygen. All right. So of course, this one is mass of aluminium over the atomic mass of aluminium, then the charge of aluminium equals to the mole of oxygen. So this time around, the mole, we are going to be using volume because you are talking in terms of volume for oxygen. So mole of oxygen is going to be the volume of oxygen over volume at STP. So since mole is volume over volume at STP, so we use that. So then the electron pass in oxygen. All right. So Now we write the equation to know the electrons. So you see that this one is what? 3 electrons. To give us aluminum solid. Then you know that oxygen is usually produced, as I said earlier, from OH, and the equation is 4OH minus, giving us 2 moles of water plus 1 mole of oxygen plus 4 moles of electrons. This is the equation for evolution of oxygen in electrolysis. So it's just like this. And so 4 is always the E whenever you're talking about oxygen. All right. Now, so the mass of aluminum, so if this one is equation 1 and this one is equation 2, therefore you substitute the values in equation 2. Therefore, equation 2 becomes what? So, what's the mass of aluminum? 3.2. What's the molar mass? The atomic mass of aluminum here is 27. You may not put the unit. Of course, you always cancel out. So now what about the electrons? The E, so it's 3, okay? Equals to what? So the volume of oxygen, that's what you have to calculate. And of course, sorry, this one should be 22.4 dm cube. So 22.4 dm cube. So, all right, so that's 22.4 dm cube times the electron in oxygen is 4. So we'll make that the subject of the equation. Make the volume of oxygen the subject of the equation. So we're gonna have 3.2 times 22.4 times 3. So divided by 27 times 4. So if you press down your calculator, so you will have 1.99 dm cube. I believe this makes life very easy. That's chemistry. Chemistry makes life very easy. You just demystify it simply as it is. All right. So I believe you've gained a lot in the course of this tutorial for today. I want you to subscribe if you have not subscribed. Share these videos with your kids, with your friends, with your bucket mates, with your slippers mates, with all your mateable mates, and let them also enjoy the simplicity that you see in Unique Chemistry School. Thank you very much. If you need an online tutorial, you can reach me via my WhatsApp number. Thank you very much. Have a great day.